Welcome to the Chill Scientist. Comment your idea for a future topic for us to cover. Let's jump right in. Quantum computing is one of those rare ideas that bridges two very different worlds. The abstract realm of quantum mechanics and the practical market-driven sphere of modern technology. For decades, the concept lived mostly in physics labs and academic journals. Today, it's not only a scientific pursuit, but also a financial one. Investors are pouring money into the field, and companies at the forefront of quantum development are seeing their stock prices climb as excitement builds around what could be the next revolution in computing. Consider IonQ, a company specializing in trapped ion quantum computers. Recently, its stock price surged after it announced acquisitions like Oxford Ionics and Vector Atomic, which could strengthen its position in hardware and control systems. D-Wave, which focuses on quantum annealing, has also seen record highs in 2025, boosted by both technological progress and renewed investor interest. Rigetti Computing, another quantum startup, gained momentum after securing U.S. Air Force research contracts, while Quantum Computing Inc., a smaller player, has experienced bursts of rapid growth as part of the broader enthusiasm. These companies don't yet rival giants like Google or IBM capability, but their rising stock prices show just how much public attention is turning toward quantum computing as a real industry rather than a theoretical dream. This financial momentum creates an unusual situation. The science is still in its infancy, but the market is already betting on its future. Investors sense that breakthroughs in quantum hardware or algorithms could change entire industries from drug discovery to cryptography. But what exactly is quantum computing? To understand why so many people, from physicists to Wall Street traders, are excited, we first need to step back and look at the foundations, the strange and counterintuitive world of quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the smallest scales: atoms, electrons, photons, and other subatomic particles. At this level, the rules are profoundly different from the ones we experience in everyday life. A particle can exist in multiple states at once, a phenomenon known as superposition. Two particles can also become linked in such a way that changing one instantly affects the other, no matter how far apart they are, a phenomenon called entanglement. These are not speculative ideas. They've been tested in laboratories countless times, confirmed with extreme precision, and now form the backbone of modern physics. For most of the 20th century, quantum mechanics was applied in passive ways. It explained why atoms emit light at certain wavelengths, why semiconductors work, and why nuclear energy is possible. The computers we use today already rely indirectly on quantum principles. Transistors, the tiny switches inside processors, are built from quantum-engineered materials. But the idea of harnessing quantum mechanics directly to perform computation is a much more recent development. Instead of just building smaller and faster transistors, what if we could design machines that obey the rules of quantum mechanics at their core? That question is at the heart of quantum computing, While a classical computer processes information in bits, which can be either 0 or 1, a qubit quantum bit can exist in a superposition of both 0 and 1 at the same time. When multiple qubits are entangled, they form an intricate web of possible states that can be manipulated simultaneously. In theory, this allows a quantum computer to solve certain problems exponentially faster than classical ones. The promise of this power is what has driven both research and investment. It's why governments are funding multi-billion-dollar national quantum initiatives, and why companies like IonQ and D-Wave have become publicly traded stocks. But for all the excitement, quantum computing remains in an early stage. Today's devices, often referred to as NISQ machines, noisy intermediate-scale quantum, are fragile, error-prone, and limited to tens or hundreds of qubits. They are powerful enough to demonstrate proof-of-concept experiments, but not yet capable of solving the biggest real-world problems. This tension between hype and reality, between potential and limitations, makes quantum computing one of the most fascinating fields in science and technology today. On the one hand, it's still experimental and full of obstacles. On the other, the potential breakthroughs are so enormous that people are willing to bet on it years, even decades in advance. In the sections ahead, we'll explore the strange physics that makes quantum computing possible, trace the history of the field from early theory to modern hardware, and consider the timelines and use cases that could define its future. We'll also look at the challenges that remain, how to scale qubits, correct errors, and make quantum computers useful outside of the lab. By the end, you'll see why this field has captured not only the imagination of scientists, but also the attention of investors, and why, for all its strangeness, quantum computing might eventually change the way we solve problems at the deepest level. Computers have shaped nearly every aspect of modern life, from smartphones in our pockets to the supercomputers that predict the weather or model new medicines. At their heart, though, all of these machines share the same foundation: the bit. A bit is the smallest unit of digital information represented as either a 0 or a 1. Inside a laptop, billions of transistors switch these bits on or off at incredible speeds, performing calculations step by step. This system is astonishingly powerful. Classical computers can simulate galaxies, crunch economic models, and stream endless libraries of video. Yet, despite their success, there are problems in science and technology that remain stubbornly beyond their reach. The first reason for these limits is scale. Classical computers process information sequentially, even if they can do so in parallel with multiple processors. When a problem involves a huge number of possibilities, the time needed to solve it can grow so quickly that even the fastest machines cannot keep up. A classic example is the problem of factoring very large numbers. Suppose you want to find the prime factors of a number with hundreds or thousands of digits. The number of possible combinations grows astronomically, and even the most advanced supercomputers would take longer than the age of the universe to finish. This difficulty is why RSA encryption, the backbone of online security, works. Classical computers simply cannot brute force their way through such a calculation. Another example comes from chemistry and physics. Molecules, especially large ones, behave according to quantum mechanics. Their electrons can interact in countless ways, creating an enormous space of possibilities that needs to be calculated. Classical computers can simulate small molecules fairly well, but as molecules get bigger, say proteins used in medicine, the task quickly becomes impossible. Even the world's best supercomputers struggle to model more than a few dozen interacting electrons with full accuracy. Since chemistry, material science, and biology all depend on understanding these interactions, the inability to model them perfectly leaves gaps in our knowledge. There's also the problem of optimization. Many real-world challenges involve finding the best solution among countless options. The most efficient route for delivery trucks in a city, the lowest energy configuration of a protein, or the best arrangement of investments in a financial portfolio. Classical computers can approximate answers, but the complexity of these problems grows so fast that exact solutions are practically impossible for large systems. These belong to what computer scientists call NP-hard problems, where the time required to compute grows faster than any reasonable computer can handle. In some cases, the issue isn't just the number of possibilities, but the nature of the calculation itself. Quantum systems are inherently probabilistic, meaning that particles don't have definite positions or energies until measured. Classical computers can try to approximate these probabilities, but they must store and track an exponential amount of information to do so. For example, if you want to describe the state of 300 interacting particles, you would need more numbers than there are atoms in the visible universe. No classical computer can ever store that much information, no matter how advanced our hardware becomes. These limits don't mean classical computing is weak. Far from it. The progress of Moore's law, doubling transistor density every couple of years, has been one of the greatest technological achievements in history. But as transistors shrink to the scale of a few nanometers, we are approaching physical boundaries. Quantum effects like tunneling already make it difficult to keep transistors functioning reliably at tiny scales. This physical reality makes it unlikely that classical computers can simply continue scaling up forever to overcome these hard problems. This is where quantum computing offers a fundamentally different approach. By using qubits instead of bits, and by leveraging phenomena like superposition and entanglement, a quantum computer doesn't need to test every possible solution one at a time. Instead, it can explore many possibilities simultaneously, using quantum interference to amplify the correct solutions and cancel out the wrong ones. In certain cases, this provides an exponential speedup, transforming problems once thought impossible into ones that could be solved in a reasonable time. It's important to emphasize, however, that quantum computers will not replace classical computers for everything. They are not simply faster computers for tasks like word processing, browsing the internet, or streaming video. Classical machines are far more practical and efficient. The promise of quantum computing lies in specific areas where classical approaches collapse under complexity: cryptography, molecular simulation, optimization, and certain types of machine learning. This distinction between the strengths of classical and quantum computing sets the stage for the field as it stands today. Classical computers are indispensable and will remain so, but they cannot tackle every problem humanity faces. Quantum computing offers a complementary tool, one designed for the hardest, most complex challenges. Understanding why classical systems hit their limits helps explain both the urgency and the hype driving the race to build quantum machines. The idea of quantum computing didn't begin in a lab filled with superconducting circuits or laser-trapped ions. It began as a question, an itch in the minds of physicists and computer scientists who realized that the rules of classical computing might not be enough to describe or simulate the natural world. One of the earliest and most influential voices was Richard Feynman, the Nobel Prize-winning physicist known for his ability to cut through complexity with blunt, almost playful clarity. In a lecture in 1981, Feynman pointed out something deeply unsettling. If nature is governed by quantum mechanics, and if classical computers cannot efficiently simulate quantum systems, then maybe the only way to simulate nature properly is with a quantum mechanical computer. His statement wasn't just a suggestion, it was almost a dare. Classical computers, he argued, would always hit a wall when trying to replicate quantum behavior. The solution was to flip the problem. Build a machine that speaks the same language as the universe itself. Around the same time, David Deutsch, a physicist at the University of Oxford, was thinking along similar lines. In 1985, he published a landmark paper describing what he called a universal quantum computer. Deutsch extended Alan Turing's famous concept of a universal machine, which underlies classical computing, into the quantum world. He showed that a quantum computer could, in principle, simulate any physical system governed by quantum mechanics. Deutsch's work gave the field a theoretical backbone, turning Feynman's intuition into a formal model. In the 1980s and 1990s, the idea of quantum computing started to gain momentum in theoretical circles, though it was often treated with skepticism. For one thing, it wasn't clear whether such machines could actually be built. Quantum states are notoriously fragile, and the idea of manipulating them precisely enough to perform calculations seemed almost impossible with the technology available at the time. Critics dismissed it as a kind of physics fantasy, something interesting to think about, but impractical in reality. But the theory had power. In the mid-1990s, researchers discovered algorithms that proved quantum computers could outperform classical ones for specific tasks. The most famous was Shor's algorithm, developed by mathematician Peter Shor in 1994. Shor showed that a quantum computer could factor large numbers exponentially faster than classical computers. This result electrified the scientific community because it directly threatened the RSA encryption system that secures online communications and financial transactions. Suddenly, quantum computing wasn't just an abstract model. It was a potential disruptor of global security. Not long after, Love Grover introduced another key algorithm in 1996. Grover's algorithm showed that quantum computers could search through unsorted databases in roughly the square root of the time required by classical computers. While this was not as dramatic as Shor's exponential speedup, it demonstrated that quantum advantages could apply more broadly than just to cryptography. These breakthroughs marked the true birth of quantum computing as a serious field of study. They proved that if such machines could be built, they would not merely be curiosities. They would have practical, world-changing power. Governments and tech companies began to take note, slowly increasing funding for research. The early 2000s saw the first experimental demonstrations of simple quantum operations, entangling a handful of qubits, running small versions of Shor's algorithm, and building basic error-correcting codes. At this stage, quantum computing was still more theory than practice. Labs could barely hold on to quantum states for more than microseconds before they collapsed due to decoherence, the tendency of quantum systems to lose their delicate properties when disturbed by the environment. Scaling from 2 or 3 qubits to dozens, let alone hundreds or thousands, seemed like an impossible leap, yet the field pressed forward, driven by the knowledge that even a small-scale quantum computer could outperform classical supercomputers for very specific problems. By the late 2000s, research groups around the world were experimenting with different physical systems for building qubits, superconducting circuits cooled near absolute zero, ions trapped and manipulated with lasers, photons sent through intricate optical circuits, and even proposals for exotic topological qubits that might be more stable than other approaches. Each method had its advantages and drawbacks, and no single path emerged as the clear winner. Despite the skepticism, the birth of quantum computing in the 1980s and 1990s set the trajectory we are still following today. It began with Feynman's bold observation, was formalized by Deutsch's universal machine, and gained urgency with Shor's and Grover's algorithms. From those seeds grew a field that is now attracting billions in investment, headlines in mainstream media, and real-world companies competing to be the first to unlock the quantum advantage. The early history of quantum computing reminds us of how science often progresses. A simple but profound question: what if we built a computer that follows the laws of quantum mechanics? Can spark decades of research, debate, and eventual breakthroughs. At first, the idea sounded impossible. Today, it is one of the most promising frontiers of technology. At the core of every classical computer lies the bit, a tiny switch that can be either 0 or 1, off or on. It's simple, elegant, and the foundation of everything from calculators to supercomputers. A qubit, or quantum bit, is both familiar and profoundly different. Like a classical bit, it has 2 possible states, 0 and 1. But thanks to the rules of quantum mechanics, a qubit can also exist in a superposition of both at once. This is not a metaphor or a trick. It's a measurable physical reality confirmed in countless experiments. To understand this, imagine you flip a coin. A classical coin is either heads or tails. A quantum coin, on the other hand, can be in a state that is partly heads and partly tails at the same time. Only when you measure it by checking the outcome does it collapse into one or the other. In computing terms, this means that a qubit can represent both 0 and 1 simultaneously, allowing quantum computers to handle many possibilities in parallel. But superposition is only half the story. Qubits can also become entangled, a phenomenon Albert Einstein once derided as spooky action at a distance. When two qubits are entangled, the state of one is linked to the state of the other, no matter how far apart they are. Measure one, and you immediately know something about the other. This interconnection allows quantum computers to perform complex operations across multiple qubits in ways classical bits never could. Entanglement is the glue that lets quantum computers scale up from individual qubits to powerful processors. Another crucial concept is interference. Quantum states behave like waves, and just as waves can amplify or cancel each other, qubit states can be manipulated so that the correct solutions to a problem are strengthened while incorrect ones fade away. This is how quantum algorithms extract useful answers from the sea of probabilities generated by superposition. The qubit is not just an abstract idea, it must be built into hardware. Over the past few decades, scientists and engineers have pursued multiple approaches, each with its strengths and challenges. Superconducting circuits. These are tiny loops of superconducting material, cooled to near absolute zero. Companies like Google, IBM, and Rigetti use this method. Superconducting qubits are relatively easy to manufacture with existing chip technology, and they can be controlled using microwaves. Their downside is fragility. Errors creep in quickly, and the qubits typically survive for only microseconds. Trapped ions. Here, individual atoms are held in place by electromagnetic fields and manipulated with lasers. IonQ and Honeywell have invested heavily in this method. Trapped ions have extremely long coherence times compared to superconducting qubits, meaning they stay stable for much longer. However, scaling up to hundreds or thousands of ions is technically complex, since each one must be controlled precisely with lasers. Photons. Light particles can also act as qubits, traveling through optical fibers and circuits. Photonic qubits have the advantage of being naturally resistant to noise and well-suited for communication, which makes them attractive for building a quantum internet. Companies like Xanadu and PsiQuantum are exploring this approach. The challenge is that building large, reliable photonic quantum computers requires advanced optical technology that is still in development. Topological qubits. This is perhaps the most exotic idea. Instead of using single particles, topological qubits would rely on quasi-particles called anyons, which exist only in 2 dimensions and have unique braiding properties. Microsoft has pursued this approach for years, believing topological qubits could be far more stable and less prone to error. But so far, clear experimental evidence of working topological qubits remains elusive. Neutral atoms and other novel methods. Some companies and labs are experimenting with using neutral atoms held in place by optical tweezers or other unconventional systems. These methods are newer, but could provide advantages in scalability and control. What all these approaches share is the enormous difficulty of keeping qubits stable. Quantum states are fragile. Any interaction with the environment, heat, stray electromagnetic fields, or even background vibrations, can cause a qubit to lose its quantum properties, a process called decoherence. Protecting qubits requires extreme environments, such as cryogenic temperatures near absolute zero or ultra-high vacuum systems. This is one reason why quantum computers look nothing like laptops. They are massive machines housed in dilution refrigerators filled with cables, lasers, and shielding. Despite these challenges, researchers have made significant progress. In the 1990s, labs could barely demonstrate a single qubit. Today, companies like IBM and Google operate devices with more than 100 superconducting qubits, while IonQ's trapped ion systems achieve high fidelity with fewer qubits. Though these machines are still far from the thousands or millions needed for practical error-corrected quantum computing, they mark a dramatic leap forward from the field's early days. The qubit, then, is both simple and revolutionary. On paper, it's just the quantum version of a bit. In practice, it requires some of the most advanced engineering humanity has ever attempted. Each method of building qubits carries trade-offs in stability, scalability, and control, and no one knows which approach or combination will win in the long run. But whichever form they take, qubits are the building blocks of a technology that promises to push computing into an entirely new domain. So far, we've explored why classical computers hit limits and what makes qubits so different. But the raw ability of qubits to exist in superposition or entangle with one another doesn't, by itself, guarantee faster computation. Without carefully designed instructions, a quantum computer would just produce a noisy jumble of probabilities. This is where quantum algorithms come in, the clever recipes that exploit quantum mechanics to do things classical computers cannot. The most famous quantum algorithm, and the one that first turned heads outside of physics circles, is Shor's algorithm. Developed in 1994 by mathematician Peter Shor, it addresses a very specific but world-shaking problem: factoring large numbers. As mentioned earlier, much of modern cryptography depends on the fact that factoring huge numbers into primes is too hard for classical computers to do efficiently. RSA encryption, for example, protects credit card transactions, online communication, and government secrets by relying on this difficulty. Shor's algorithm showed that a sufficiently powerful quantum computer could factor large numbers exponentially faster than classical methods. The core insight is that quantum computers can use period finding, a kind of mathematical rhythm hidden in the structure of numbers, combined with interference to rapidly identify factors. The details are mathematically complex, but the result is simple. Encryption schemes that depend on the hardness of factoring could be broken. Suddenly, what had been a purely academic idea had a profound implication for global security. Governments and cybersecurity experts took notice immediately. Just 2 years later, in 1996, Love Grover proposed another quantum algorithm that expanded the possibilities. Grover's algorithm addresses search problems. Suppose you have an unsorted database with n items, and you want to find the one item that matches a certain condition. A classical computer might have to check, on average, about half the items before it succeeds. Grover's algorithm, however, can find the answer in roughly square root of n steps. That doesn't sound dramatic at first, but for huge data sets, the difference is enormous. If you had 1 billion items, a classical search might take 500 million tries on average. Grover's would need only about 31,000. This is not as powerful as Shor's exponential speedup, but it applies to a much broader range of problems. Together, Shor's and Grover's algorithms prove that quantum computing was not just theoretical curiosity. They gave concrete examples of problems where quantum systems could outperform classical ones in ways that mattered. This set off waves of research. Scientists began looking for other algorithms that could leverage quantum mechanics for advantages in optimization, simulation, and machine learning. One important class of algorithms involves quantum simulation. Since the original motivation for quantum computing was Feynman's idea that only quantum machines can simulate quantum systems efficiently, this area remains a central goal. Quantum simulation algorithms allow researchers to model molecules, materials, or chemical reactions far beyond the reach of classical supercomputers. Imagine being able to design new drugs by simulating how a protein folds, or building new types of batteries by understanding their quantum chemistry at the atomic level. These are not futuristic dreams. They are the kinds of problems current quantum hardware is beginning to target. Another major area is optimization. Many real-world problems, from logistics to finance, involve finding the best solution among countless possibilities. Quantum algorithms like the quantum approximate optimization algorithm, QAOA, and the variational quantum eigensolver, VQE, combine classical and quantum resources to approach these challenges. These others are especially important in the current era of NISQ devices, which are noisy and limited, but still capable of running hybrid algorithms. It's worth stressing that not every problem becomes easier with quantum computing. For tasks like basic arithmetic or browsing the internet, quantum computers offer no advantage. Their strength lies in very particular domains where classical approaches collapse under exponential complexity. This is why the discovery of Shor's and Grover's algorithms was so groundbreaking. They showed where quantum advantages actually exist. Quantum algorithms are also deeply tied to the physics of qubits, unlike classical algorithms, which can be written in software and run on any hardware. Quantum algorithms depend on manipulating fragile quantum states with precision. Implementing Shor's algorithm on a real machine requires thousands, perhaps millions, of stable, error-corrected qubits, far beyond what we currently have. In contrast, algorithms like VQE are designed to run on today's smaller, noisier devices, making them a practical bridge between theory and application. These discoveries reshaped the field. Before the mid-1990s, quantum computing was interesting but abstract. To Shor and Grover, it became urgent. Governments began funding quantum research at higher levels, and private companies started to explore potential applications. The algorithms gave the field direction, transforming it from speculative theory into a roadmap with real stakes: breaking encryption, simulating nature, optimizing the complex systems that underpin modern society. Quantum algorithms represent the brain of a quantum computer. Without them, qubits are just strange particles in strange states. With them, they become tools for solving problems once thought unreachable. The discovery of these algorithms was the spark that ignited the race we see today, one that spans not only physics labs, but also stock markets, global industries, and national security agencies. If there's one word that haunts the dreams of quantum engineers, it's decoherence. Quantum states are delicate by nature. A qubit may exist in a perfect superposition, entangled with others in a carefully choreographed dance, but the slightest interaction with the outside world, heat, stray electromagnetic fields, cosmic rays, even vibrations from the building around it, can destroy that fragile state in an instant. When this happens, the qubit collapses into an ordinary 0 or 1, losing the very quantum properties that make it valuable. This fragility is what makes building a useful quantum computer so difficult. Classical bits are robust. You can flip them on and off billions of times per second with near-perfect reliability. Qubits, by contrast, can hold onto their quantum state only for limited periods, called their coherence time. For superconducting qubits, this may be only microseconds to milliseconds. Trapped ions can last longer, but even they eventually succumb to noise. And when you're trying to run a sequence of thousands or millions of quantum operations, those tiny windows of stability are simply not enough. The solution, at least in theory, lies in quantum error correction. In classical computing, error correction is relatively straightforward. You can duplicate bits, add parity checks, or use redundancy to detect and fix mistakes. With quantum systems, things get trickier. You cannot simply copy qubits. The no-cloning theorem of quantum mechanics forbids making identical copies of an unknown quantum state. Instead, error correction involves spreading the information of one logical qubit across many physical qubits, creating redundancy through entanglement rather than duplication. One of the earliest and most influential error-correcting schemes is the Shor code, which encodes a single qubit into 9 physical qubits in such a way that errors can be detected and corrected without directly measuring and collapsing the state. Since then, more advanced codes have been developed, such as the surface code, which is now considered one of the most promising approaches. The surface code uses a lattice of qubits arranged in 2 dimensions, where stabilizer measurements check for errors in groups without disturbing the overall state. The catch, of course, is scale. Implementing error correction requires a huge overhead. To create one logical qubit, a qubit that is stable and reliable enough to perform long calculations, you may need hundreds or even thousands of physical qubits, depending on how noisy the system is. That means a useful, large-scale quantum computer capable of running algorithms like Shor's may require millions of qubits, far beyond the tens or hundreds we currently have. In practice, researchers focus on extending coherence times and reducing error rates so that fewer physical qubits are needed. Superconducting systems now achieve gate fidelities above 99%, and trapped ion systems can sometimes do even better. But even with such high accuracy, the accumulation of tiny errors across thousands of operations still makes error correction essential. There are 2 main types of errors quantum computers must contend with. 1, bit flip errors, where a qubit accidentally flips from 0 to 1 or vice versa. 2, phase flip errors, where the relative phase of a superposition state is altered, scrambling the interference patterns algorithms rely on. Error correction codes are designed to detect and fix both kinds without collapsing the underlying quantum information. It's a delicate balancing act. You want to gather enough information to know whether an error has occurred, but not so much that you destroy the quantum state you're trying to preserve. Another way to combat decoherence is through better qubit design. For example, some superconducting qubits are engineered to be less sensitive to noise by carefully shaping their energy landscapes. Trapped ion qubits benefit from the fact that ions are identical and well isolated, making them naturally more stable. Photonic qubits, meanwhile, can travel long distances with minimal loss, though scaling them for computation poses challenges of its own. Despite the difficulties, progress is real. In 2023, researchers at Google demonstrated a milestone by showing that error-corrected logical qubits could outperform the raw physical qubits they were built from, a small but critical proof that error correction works in practice. IBM has also published detailed roadmaps outlining how they intend to scale from today's noisy devices toward fault-tolerant quantum computers by the 2030s. Still, the gap remains wide. For now, we are in the NISQ era, noisy intermediate-scale quantum, where devices are powerful enough to run experiments, but not yet capable of fault-tolerant, large-scale computation. The NISQ era is both frustrating and exciting. Frustrating because we don't yet have the machines needed to fully unleash algorithms like Shor's. But exciting because researchers are inventing clever hybrid approaches to make use of the noisy devices we do have. Decoherence and error correction may not sound as thrilling as quantum algorithms or futuristic applications, but they are the heart of the engineering challenge. Without solving them, quantum computing remains a fragile laboratory curiosity. With them, it could become one of the most powerful technologies in human history. The struggle against decoherence is the battlefield on which the future of quantum computing will be won or lost. For years, quantum computing existed mainly on whiteboards and in scientific papers. But in the last 2 decades, the field has shifted from abstract theory to working hardware. These machines are still small, fragile, and noisy, but they represent the first real attempts to turn qubits from laboratory curiosities into usable computing resources. Today, there are several competing approaches to building quantum hardware, each with different advantages and trade-offs. No one knows which method or combination will ultimately dominate, but the diversity of experiments is a strength. It means the field is not locked into one path, but is instead exploring multiple ways forward. Superconducting qubits. Superconducting circuits are currently the most developed approach, pursued by giants like IBM, Google, and Rigetti. These qubits are built from tiny electrical loops made of superconducting materials cooled to near absolute zero in massive dilution refrigerators. Microwaves are used to manipulate the qubits, flipping them between states or entangling them. IBM has laid out one of the most detailed roadmaps in the industry. In 2019, their 53-qubit quantum canary processor was a milestone, and by 2023 they had unveiled Condor, a 1,121-qubit chip. While not all those qubits are usable for error-corrected computation, the sheer scale demonstrates rapid progress. IBM also offers access to smaller quantum devices through its IBM Quantum Experience Cloud platform, allowing researchers and even students worldwide to run experiments. Google, meanwhile, made headlines in 2019 with its claim of quantum supremacy. Using its 53-qubit Sycamore processor, Google performed a highly specific calculation, sampling from a distribution of random numbers in about 200 seconds, something they estimated would take a classical supercomputer thousands of years. While some disputed the claim, arguing that classical algorithms could do it faster than Google suggested, the demonstration was still a watershed moment. The first time a quantum device definitively outperformed a classical one in a controlled experiment. Rigetti, a startup based in California, has also developed superconducting qubit processors and offers them through its Quantum Cloud Services platform. While smaller in scale than IBM or Google, Rigetti has focused on making quantum hardware accessible to commercial and government partners. Trapped ion qubits, another leading approach, uses trapped ions, pursued by companies like IonQ and Quantinuum. In these systems, individual atoms, often ytterbium or calcium, are suspended in electromagnetic fields and manipulated with lasers. Each ion serves as a qubit with quantum states encoded in its electronic or vibrational levels. Trapped ions have some of the best coherence times of any qubit technology, often lasting seconds or even minutes, vastly longer than superconducting qubits. They also achieve very high gate fidelities, making them reliable for small-scale computations. The trade-off is speed and scalability. Operations with trapped ions are slower, and controlling many ions in a single trap becomes increasingly difficult. IonQ currently operates systems with a few dozen qubits, but claims that its technology scales more naturally than superconductors. Photonic qubits. Companies like PsiQuantum and Xanadu are betting on photons, particles of light, as qubits. Photons are naturally resistant to noise, and because they don't easily interact with their environment, they can maintain coherence over long distances. This makes photonic systems especially attractive for quantum communication and networking. PsiQuantum, for example, has set an ambitious goal of building a 1,000,000-qubit machine using photonic circuits integrated with conventional semiconductor manufacturing. While still in early stages, the approach promises massive scalability if the engineering challenges can be solved. Neutral atoms and exotic approaches. Some companies and research groups are exploring neutral atoms held in place by optical tweezers. By arranging hundreds of atoms in grids and controlling them with lasers, scientists can create flexible, reconfigurable arrays of qubits. This approach is newer, but has shown promising results in scaling up quickly. Microsoft has staked its bet on topological qubits, a highly theoretical idea based on exotic quasi-particles that would be inherently more stable against noise. While this approach could in principle solve many of the challenges of error correction, progress has been slow, and experimental confirmation remains elusive. The NISQ era. No matter which hardware you look at, one thing is clear. We are firmly in the NISQ era, the age of noisy intermediate-scale quantum computers. Current devices have between tens and a few hundred qubits, and while they can run experiments that demonstrate quantum principles, they are not yet powerful enough to solve the world's hardest problems. Their qubits are noisy, their coherence times are short, and error correction overhead remains too high for practical use. That said, the existence of these machines is revolutionary. 10 years ago, the idea of controlling 50 or 100 qubits in a lab would have seemed like science fiction. Today, researchers around the world can log into quantum processors via the cloud and run real quantum circuits. Companies are experimenting with hybrid algorithms that combine classical and quantum resources to tackle problems in chemistry, optimization, and machine learning. Quantum hardware today is a bit like aviation in the early 20th century. Fragile, limited, and experimental, but proof that flight is possible. The machines we have are not yet the quantum equivalents of passenger jets or rockets, but they are biplanes lifting off the ground, showing that the principles work. With each year, coherence times improve, qubit counts rise, and fidelity edges closer to the thresholds needed for error correction. The field is moving fast. Investors are backing companies, governments are funding programs, and researchers are refining every part of the hardware stack. The machines we have now may be noisy and limited, but they are the foundation for what could become one of the most transformative technologies of the century. For decades, quantum computing lived mostly in the world of theory, with promises of extraordinary speedups, but little to show in practice. That changed in 2019 when Google announced that it had achieved something it called quantum supremacy. The phrase, controversial and perhaps poorly chosen, meant that for the first time, a quantum computer had performed a task no classical computer on Earth could feasibly replicate in a reasonable time. The experiment used Google's Sycamore processor, a superconducting chip with 53 qubits. The task it performed was not particularly useful. It generated samples from a complex distribution of random numbers by running a series of quantum operations and measuring the outcomes. Google reported that Sycamore completed the job in about 200 seconds. They estimated that the world's most powerful classical supercomputer at the time, Summit, would have needed 10,000 years to achieve the same result. This announcement made headlines worldwide. For quantum researchers, it was proof that a quantum device could decisively outperform classical hardware, even if only for a narrow, contrived problem. For investors and governments, it was a signal that quantum computing had left the realm of speculation and entered experimental reality. Not everyone agreed with Google's framing, however. IBM published a response arguing that with clever optimization, a classical supercomputer could perform the same calculation in a matter of days, not millennia. Critics also pointed out that the problem Google chose had little real-world application. It was a demonstration of raw power, not practical utility. Still, the symbolic importance of the achievement was hard to deny. It was like the Wright brothers' first flight. Not practical, not long, but undeniable evidence that the principles worked. Google was not alone in pushing boundaries. In 2020, a team of Chinese researchers at the University of Science and Technology of China, USTC, claimed their own form of quantum supremacy using a different approach: photonic quantum computing. Their machine, called Zhuzhang, used 76 photons to perform a type of calculation known as Gaussian boson sampling, a problem so complex that classical simulations become unmanageable. The researchers reported that Zhuzhang completed the task in about 200 seconds, which they claimed would take the most advanced classical supercomputer 2.5 billion years. This result underscored two things. First, that different hardware platforms could achieve supremacy-like demonstrations. And second, that the global race for quantum computing was not confined to the United States. China's rapid progress showed that the field was now a truly international competition, with multiple countries striving for breakthroughs. So, in 2021, the same Chinese group unveiled Zhuzhang 2.0 with improved capabilities, again performing boson sampling tasks far beyond classical reach. Meanwhile, other labs continued to refine their systems, aiming to expand from contrived demonstrations toward algorithms with real-world applications. It's worth pausing to consider what quantum supremacy really means. The term suggests a kind of ultimate victory, but in reality, it refers to a specific milestone. When a quantum computer can solve any problem that classical computers cannot do in a reasonable time, It does not mean quantum computers are now broadly useful or that they have overtaken classical machines across the board. Supremacy is like crossing a threshold. It proves quantum devices can, in principle, do something fundamentally new. The real challenge is translating that ability into practical impact. Some researchers prefer the term quantum advantage, which emphasizes usefulness over raw performance. Achieving advantage means using quantum computers to solve practical problems better than classical methods, whether in chemistry, optimization, or machine learning. Unlike supremacy, which has already been demonstrated in narrow cases, quantum advantage remains an open frontier. These experiments have had lasting consequences. They drew public attention, inspired new funding, and attracted talent to the field. They also highlighted the challenges ahead: noisy devices, error correction, and the gulf between theoretical algorithms and real-world implementation. But they proved the point that quantum computing is not just theory. The machines exist, they can run, and they can do things classical computers cannot. As more groups demonstrate increasingly complex experiments, sometimes with hundreds of qubits, sometimes with new physical systems, the race continues. The term quantum supremacy may fade from the headlines, but the underlying reality remains. Quantum hardware has crossed the line from speculation to demonstration. The next milestone is clear. Moving from supremacy to advantage, from proof of principle experiments to solving problems that matter. Whenever people talk about quantum computing, one of the first questions that comes up is, what can it actually do? Demonstrations like Google's supremacy experiment or China's photonic sampling machine are impressive, but they don't immediately solve real problems. The real value of quantum computing lies in the future, what it will enable once the hardware matures and the algorithms are applied to areas where classical computers fall short. Researchers and companies have identified several domains where quantum advantage could emerge first. 1. Chemistry and material science. Perhaps the most natural use of quantum computers is simulating quantum systems themselves. Molecules, materials, and chemical reactions are governed by quantum mechanics. And as molecules get larger, classical computers struggle to model them accurately. Quantum computers, by contrast, are built on the same rules that molecules follow. This makes them ideally suited for exploring problems such as designing new drugs by modeling how proteins fold and interact, developing better catalysts for industrial processes, including fertilizer production and carbon capture, creating new materials for energy storage, like high-capacity batteries or superconductors. Even modest quantum devices, if carefully optimized, could begin to handle molecules beyond the reach of classical simulation. Companies like QSimulate, Zapata, and partnerships between quantum startups and pharmaceutical firms are already exploring these directions. 2. Optimization problems. Optimization problems are everywhere. Logistics companies trying to route fleets of trucks efficiently, airlines scheduling flights, manufacturers managing supply chains, or financial institutions balancing risk and return in portfolios. These problems are hard because the number of possible arrangements grows exponentially as the system scales. Quantum algorithms, like the quantum approximate optimization algorithm, QAOA, aim to provide better solutions faster by exploring many possibilities simultaneously and using interference to steer toward the best outcome. For industries where small improvements translate into big savings, like cutting fuel costs by just a few percent, quantum optimization could have huge economic impact. Some of these applications may be among the first to show practical quantum advantage, especially when combined with classical pre- and post-processing. 3. Machine learning and AI quantum computing also holds promise in machine learning, though this area is less clearly defined. The hope is that quantum computers could accelerate training or improve pattern recognition by processing high-dimensional data in ways classical systems cannot. For example, quantum kernels and variational algorithms could help classify data more efficiently or enable entirely new forms of neural networks. This is an area where hype sometimes outpaces reality. Many proposed quantum machine learning techniques remain theoretical, and current devices are too small to outperform classical deep learning systems. Still, the possibility of combining quantum computing with AI has drawn enormous interest, and some hybrid algorithms already show potential for niche use cases. 4. Finance and risk analysis. The financial sector is always interested in technologies that can model uncertainty and optimize portfolios more effectively. Quantum computers could help simulate complex financial systems, evaluate risk under many scenarios, or optimize trading strategies. Companies like Goldman Sachs, J.P. Morgan Chase, and HSBC have active quantum research teams, often in collaboration with hardware providers like IBM and D-Wave. 5. Cryptography and security. While not exactly a use case in the positive sense, cryptography is one of the most widely discussed areas of impact. Shor's algorithm threatens to break RSA encryption once large-scale quantum computers are available. This has spurred the development of post-quantum cryptography, a new generation of encryption algorithms designed to resist both classical and quantum attacks. Governments and standards bodies are already working to roll out these new methods, anticipating the day when quantum computers pose a real threat to current security systems. 6. Scientific research beyond chemistry. Quantum computers could also be powerful tools for fundamental science. They could model exotic states of matter, simulate quantum field theories, or explore high-energy physics scenarios that are impossible to replicate in labs. For astrophysics, they might help model black holes or the behavior of matter under extreme conditions. These applications may be farther off, but they highlight how quantum computing could expand knowledge in ways that classical computing cannot. It's important to keep expectations grounded. Most of these use cases are still aspirational. The hardware we have today cannot yet deliver practical solutions in these domains, and it will take years of progress in qubit stability, error correction, and quantum error correction and scaling before the first real-world advantages appear. But the roadmap is clear. Quantum computers are not meant to replace classical ones for everyday tasks. They are specialized tools designed for the hardest problems, the ones that explode in complexity and defy classical brute force. The excitement surrounding these potential applications is part of why investors and governments are pouring money into the field. The first company or country to achieve practical quantum advantage in areas like drug discovery or optimization could unlock massive competitive advantages. The stakes are high, not only scientifically but economically and strategically. So, while the use cases remain on the horizon, they provide the guiding light for the entire field. Every qubit added, every error reduced, every algorithm refined is a step toward turning these possibilities into realities. Quantum computing is not about making your phone faster. It's about solving problems that classical computers will never touch and opening doors into realms of science and technology that remain closed today. Of all the implications of quantum computing, few have drawn as much attention or as much fear as its potential to break modern cryptography. The security of the internet, financial systems, and even national defense rests on mathematical problems that are difficult for classical computers to solve. Quantum computers, armed with the right algorithms, threaten to upend that foundation. Most digital communication today relies on public key cryptography, also known as asymmetric encryption. The most widely used scheme is, say, encryption, which secures everything from credit card transactions to private emails. The system works by generating two keys, a public key used to encrypt data and a private key used to decrypt it. RSA security depends on the difficulty of factoring large numbers into their prime components. For example, multiplying two enormous prime numbers is easy, but reversing the process, figuring out which primes produce the result, is extremely hard for classical machines once the numbers grow large enough. Enter Shor's algorithm, discovered in 1994. As explained earlier, Shor showed that a quantum computer could factor large numbers exponentially faster than classical methods. This means that once large-scale, error-corrected quantum computers are available, they could break RSA encryption in a matter of hours or days. What today would take billions of years on a supercomputer would suddenly become tractable. The same applies to related schemes like Diffie-Hellman key exchange and elliptic curve cryptography. The threat is not theoretical. It's a ticking clock. We don't yet know when large quantum computers capable of running Shor's algorithm will exist, but governments and security experts are already preparing. If encrypted data today is intercepted and stored, it could be decrypted in the future once quantum machines catch up. This is sometimes called a store now, decrypt later attack, and it means that even if quantum computers are 10 or 20 years away, the information being transmitted right now could eventually be exposed. To address this, the field of post-quantum cryptography, PQC, has emerged. These are new cryptographic schemes designed to resist both classical and quantum attacks. They're typically based on mathematical problems that quantum computers are not known to solve efficiently, such as lattice-based cryptography, hash-based signatures, and multivariate polynomial equations. The U.S. National Institute of Standards and Technology, NIST, has been leading a multi-year effort to evaluate and standardize post-quantum algorithms. In 2022, NIST announced the first group of finalists, including algorithms like Crystal's Kyber for encryption and Crystal's dilithium for digital signatures. These schemes are expected to replace RSA and elliptic curve systems over the next decade. Governments worldwide are beginning to mandate post-quantum readiness, and companies are starting to test migrations. It's worth noting that symmetric cryptography, like AES, Advanced Encryption Standard, is less vulnerable. Quantum computers running Grover's algorithm can speed up brute force key searches, but only quadratically. That means doubling the key length from 128 bits to 256 bits, provides sufficient security even against quantum attacks. So, while public key systems need a complete overhaul, symmetric encryption remains relatively safe with modest adjustments. Quantum technology also brings opportunities for new forms of security. Quantum key distribution, QKD, for example, uses the principles of quantum mechanics to allow two parties to share a secret key in such a way that any eavesdropping attempt will be detectable. QKD has already been demonstrated in labs and even via satellites in China's Macias project, which established secure links over thousands of kilometers. While QED is not a replacement for all cryptography, it requires specialized infrastructure and is limited in scalability. It shows how quantum mechanics can protect information as well as threaten it. The looming impact on cryptography is one of the reasons governments are so invested in the quantum race. A nation that builds a large-scale quantum computer before others could potentially decrypt rivals' communications, undermining global security. This is why agencies like the NSA, GCHQ, and their counterparts in China and Europe are closely watching quantum progress and pushing for rapid adoption of post-quantum standards. For the general public, the transition to quantum-safe cryptography will likely happen quietly in the background, much like past shifts in security standards. Software updates, new protocols, and upgraded certificates will gradually roll out across the internet. But for industries handling sensitive information, finance, healthcare, defense, the transition is urgent. The data being generated today must remain secure, not just now, but decades into the future. In the end, quantum computing doesn't just threaten existing security, it reshapes the entire conversation around it. The same technology that can break RSA could also enable unbreakable communication channels. It forces us to rethink how we protect information in a world where the computational assumptions of the past no longer hold. It's tempting to think of quantum computers as supercomputers, machines destined to replace the most powerful classical systems. But the truth is more nuanced. Quantum and classical computing are not enemies locked in a zero-sum fight. Instead, they are complementary tools, each with unique strengths and weaknesses. To understand where quantum machines fit, it's useful to compare them directly with classical supercomputers. The power of classical supercomputers are marvels of engineering. Machines like Japan's Fugaku, the US's Frontier, and China's Sunway Taihu Light can perform quadrillions of operations per second. They are built from millions of interconnected classical processors, optimized for speed, reliability, and parallelism. These systems excel at tasks like weather prediction and climate modeling, simulating airflow for aerospace engineering, processing massive amounts of genomic data, training advanced artificial intelligence models. The advantage of classical machine is their maturity. They've been optimized for decades, and their reliability is unmatched. They can run almost any algorithm, handle diverse data, and provide predictable performance. Importantly, they are general purpose, while quantum devices are highly specialized, the limits of classical systems. But even supercomputers hit walls. Some problems scale so badly that even with millions of processors, they remain intractable. For example, simulating a complex molecule or modeling the quantum behavior of materials requires exponential resources as the system grows. A molecule with just 50 interacting electrons may already be beyond the reach of the best classical machines. In optimization problems, the number of possible configurations often grows faster than classical brute force can manage. No matter how many processors are thrown at it, the quantum advantage. This is where quantum computing shines. Because qubits can exist in superposition and entangle with one another, quantum systems can explore exponentially many states in parallel. Algorithms like Shor's for factoring or VQE for molecular energy calculations exploit this feature to outperform classical methods. Quantum computers don't need to simulate quantum mechanics. They are quantum systems. This makes them uniquely powerful for chemistry, materials science, cryptography, and certain optimization tasks. In these niches, quantum advantage could eventually outpace anything a classical supercomputer could achieve. The NISQ reality check. That said, today's quantum devices are not yet replacements for classical machines. We are still in the NISQ era, noisy, intermediate-scale quantum, where qubits are fragile, coherence times are short, and error correction is incomplete. Current quantum computers can't outperform classical supercomputers on practical tasks. In fact, supercomputers are often used to simulate quantum devices themselves, helping researchers design better qubits and error correction codes. In many cases, hybrid approaches are emerging. Classical and quantum computers can work together, with the quantum processor handling the hard quantum core of a problem, while the classical system manages everything else. For example, in variational quantum algorithms, a quantum device prepares candidate states, while a classical computer evaluates and adjusts parameters. This partnership is likely to define the near future of quantum computing, the coexistence model. The future will not be quantum machines replacing classical ones wholesale. Instead, think of quantum computers as specialized accelerators, much like GPUs today. Graphics processing units didn't replace CPUs, they complemented them, accelerating specific tasks like rendering and deep learning. Similarly, quantum processors may sit alongside classical supercomputers, handling the parts of problems where quantum advantage exists. Supercomputers will still dominate general-purpose tasks, running weather models, simulating earthquakes, analyzing large-scale economic data, or training next-generation AI. Quantum computers, once error-corrected and scaled, will step in for targeted problems, breaking encryption, simulating complex molecules, optimizing huge networks, or probing the deep mysteries of physics. Why both matter. It's also worth noting that classical computing is far from done. Advances in chip design, parallelism, and even experimental classical technologies like neuromorphic computing continue to push the boundaries of what's possible. Just as quantum machines are advancing, so too are classical ones. The two fields are evolving in tandem, often helping each other. In short, quantum computing is not the next generation of classical computing. It's a new branch altogether, just as airplanes didn't make ships obsolete but expanded humanity's transportation toolkit. Quantum computers will expand our computational toolkit. Together with classical systems, they will form a complementary ecosystem designed to handle problems across the spectrum of science, engineering, and security. Quantum computing is one of those rare fields where the line between science fiction and scientific reality feels paper thin. Over the last few decades, the progress has been staggering, shifting from theoretical equations on paper to actual hardware that you can rent through the cloud. Yet, we're still at the beginning of the journey. The road ahead is filled with both breakthroughs and challenges, hype and hard engineering. To understand where things may go, it helps to look at timelines, competition, and what realistic expectations look like. The timeline debate. Ask 10 experts when we'll have large-scale, fault-tolerant quantum computers, and you'll get 10 different answers. Some optimists predict within a decade. Others say 20 to 30 years. A few skeptics suggest it may never fully materialize. The truth likely lies somewhere in the middle. Recent progress in scaling qubits and error correction shows that milestones once thought impossible are being crossed. IBM, for instance, has publicly committed to building systems with thousands of qubits by the late 2020s and aims for error-corrected devices in the 2030s. Google has laid out similar goals. Whether these roadmaps hold is an open question, but the ambition is clear. In the near term, we remain in the NISQ era, noisy intermediate-scale quantum. Over the next 5 to 10 years, expect to see growing demonstrations of hybrid quantum classical algorithms solving small but meaningful problems. Industries like chemistry, logistics, and finance will likely be the first to experiment seriously with quantum solutions, not because they're perfect, but because even incremental gains can have large impacts. By the 2030s, if progress continues, fault-tolerant quantum machines could arrive, capable of running algorithms like Shor's at scale. This is when the cryptographic threat becomes real, and when more ambitious applications, like simulating complex materials or breaking into optimization at industrial scales, could come into play. Beyond that, the horizon extends toward millions of qubits, opening possibilities we can barely imagine today. The global race quantum computing is no longer just a scientific endeavor, it's a geopolitical race. The United States, China, Europe, and other regions are pouring billions into quantum research. China's photonic supremacy demonstrations showed it is a major player. The European Union has launched its own large-scale quantum initiatives. The U.S. government funds research through agencies like DARPA and the National Science Foundation, while companies like IBM, Google, and IonQ push forward in the private sector. The stakes are enormous. A nation that achieves large-scale quantum computing first could gain strategic advantages in cybersecurity, drug discovery, materials science, and finance. It's no surprise that quantum computing is often described as the next technological arms race, with national security implications alongside commercial ones. The role of industry startups and big tech companies alike are driving innovation. IonQ, Rigetti, PsiQuantum, Xanadu, and others are exploring diverse hardware approaches, while cloud providers like Amazon and Microsoft are integrating quantum access into their platforms. Pharmaceutical companies, banks, and logistics firms are already running pilot projects, hoping to gain an early foothold. Stock markets reflect this excitement. Companies like IonQ, traded under IonQ, and D-Wave, QBTS, have seen surges in value as investors speculate on quantum's potential, while some of this may be fueled by hype. It also underscores the growing public interest and confidence in the field. The hype and the reality quantum computing is hyped, no doubt. Headlines often overstate breakthroughs, and timelines are sometimes presented as if practical, world-changing quantum computers are just around the corner. The reality is more complex. Progress is steady but incremental. Each milestone, more qubits, higher fidelities, better error correction, takes years of effort. It's crucial to balance optimism with patience. What's undeniable, though, is that the field is moving forward. The dream is not static. It's evolving with every experiment and every paper published. The hardware gets better. The algorithms get sharper. The ecosystem grows richer with researchers, engineers, and investors. A dual future. Looking ahead, the most realistic vision is not quantum computers replacing classical ones, but both working together. Quantum processors will become specialized accelerators, tackling specific tasks in partnership with classical supercomputers. This hybrid model will dominate until, and maybe even after, full-scale, fault-tolerant systems arrive. The next 2 decades will likely see a gradual unfolding of quantum advantage, first in narrow, specialized problems, then in broader applications as error correction improves. Along the way, the field will create new industries, new career paths, and new ethical questions about security, privacy, and access. The big picture. In the long run, quantum computing could be as transformative as electricity, the internet, or classical computing itself. It could change how we discover medicines, design materials, secure information, and even understand the universe. But it's not a switch that flips overnight. It's a slow build, one milestone at a time, one qubit at a time. So the road ahead is clear in one sense. Quantum computing is coming, but it's coming step by step, not in a single leap. The journey may take decades, but if history is any guide, when humanity sets its mind to cracking a grand challenge, progress happens faster than we expect. The first primitive quantum machines are already here. The next chapter, one where they become indispensable tools, is only beginning. When people hear quantum computing, they often imagine futuristic processors locked away in cryogenic chambers. But there's another frontier developing alongside computation: quantum communication. Just as the internet transformed classical computing, the concept of a quantum internet is emerging, an interconnected system that uses the principles of quantum mechanics to transmit and protect information in ways classical networks never could. At the heart of quantum communication is entanglement. As discussed earlier, entangled particles share correlations so strong that measuring one instantly affects the other, no matter how far apart they are. In networking, this can be used to create unhackable communication. Channels. If two parties share entangled qubits, any attempt by a third party to intercept or tamper with the channel immediately disrupts the entanglement and reveals the intrusion. This principle underlies quantum key distribution, QKD, one of the first real-world applications of quantum mechanics in security. QKD allows two users to generate a shared secret encryption key over a public channel. The most famous protocol is BB84, proposed in 1984 by Charles Bennett and Gilles Brassard. In BB84, photons are sent through a channel in random quantum states. Because quantum states cannot be copied without disturbance, thanks to the no-cloning theorem, any eavesdropping attempt changes the transmission in detectable ways. Once the sender and receiver confirm that no tampering has occurred, they can use the key to encrypt their communication with classical methods. QKD has moved from theory to practice. China has been especially aggressive in this area, launching the Mickey's satellite in 2016 to demonstrate long-distance quantum communication. Mickey's established entangled links over 1,200 kilometers, about 750 miles, between ground stations, proving that quantum secure communication is possible at intercontinental distances. In 2017, the satellite even facilitated the first quantum encrypted video call between China and Austria. Since then, China has built a quantum communication backbone spanning thousands of kilometers on the ground, connecting cities with quantum-secure channels. Europe and the U.S. are also investing in quantum networking. The European Union has launched the EuroQCY, Quantum Communication Infrastructure Initiative, aiming to create a pan-European quantum secure network. In the United States, the Department of Energy and several national labs are exploring prototypes of quantum internet nodes with the long-term vision of connecting quantum computers across distances. Beyond QKD, there are more ambitious visions of what a quantum network could do. One is distributed quantum computing, where separate quantum devices link together to act as a larger virtual machine. By entangling qubits across distant processors, you could, in theory, scale beyond the limitations of a single chip. This could dramatically accelerate the path to useful quantum computation. Another potential use is in clock synchronization and sensing. Entangled particles could allow distant atomic clocks to sync with unprecedented precision, improving GPS systems, financial networks, and scientific experiments. Quantum sensors linked through networks could detect tiny changes in gravitational fields, aiding fields like geology and astrophysics. Of course, there are major hurdles. Distributing entanglement over long distances is extremely difficult because photons carrying quantum information can be lost in optical fibers or corrupted by noise. In classical networks, signals can simply be copied and amplified with repeaters. But in quantum systems, the no-cloning theorem prevents straightforward amplification. The solution may be quantum repeaters, devices that extend the reach of entanglement by creating and linking shorter entangled segments. Building reliable repeaters is one of the toughest challenges in quantum networking research. Another issue is integration. Classical internet infrastructure is vast and deeply entrenched. Creating a parallel quantum internet won't replace it, but rather supplement it. Most likely, quantum communication will initially serve specialized niches, such as government communications, financial transactions, and sensitive research data, where absolute security is critical. Over time, as costs drop and technology matures, broader adoption may follow. The phrase quantum internet might sound futuristic, but the groundwork is being laid right now. Research groups are demonstrating entanglement across citywide fiber networks. Satellites are proving intercontinental QKD, and test beds are springing up in North America, Europe, and Asia. If classical computing was shaped by the rise of the internet, it's possible that quantum computing will be shaped by the rise of its own unique network infrastructure. In the end, quantum communication is about more than just security. It represents a new way of thinking about how information can move. By harnessing entanglement, superposition, and the uncopyable nature of quantum states, we may build networks that are not only faster and more secure, but fundamentally different from the systems we use today. Just as the classical internet transformed society in ways no one foresaw, the quantum internet may reshape the digital landscape in ways we're only beginning to imagine. If there is one application that almost everyone in the field agrees will be the first killer app of quantum computing, it is quantum simulation. From the very beginning, Richard Feynman's original motivation in 1981 was simple. Classical computers struggled to simulate quantum systems, so why not use quantum systems themselves to do the job? The challenge is clear. Atoms, molecules, and materials all obey the rules of quantum mechanics. The wave functions that describe them scale in complexity exponentially with the number of particles involved. A molecule with just 50 electrons already requires more memory than exists in the world to simulate fully on a classical supercomputer. This makes exact modeling impossible for anything beyond the smallest molecules. Chemists and materials scientists instead rely on approximations, which work in some cases but fall apart when the systems get too complex. Why quantum simulation matters. If quantum computers can model these systems directly, the potential is enormous. Consider drug discovery. Designing a new medicine often involves trial and error, with chemists synthesizing and testing thousands of compounds in the lab. A quantum simulator could predict how a drug molecule binds to a protein target before a single experiment is run, saving years of effort and billions of dollars. The same applies to materials science. Imagine simulating new types of superconductors that work at room temperature, revolutionizing energy transmission and storage, or design better catalysts for industrial chemistry, making processes like fertilizer production more energy efficient. Even battery technology could see breakthroughs, with quantum computers helping us design materials for longer-lasting, higher-capacity energy storage. Current approaches. Two of the leading algorithms for quantum simulation are variational quantum eigensolver, VQE, a hybrid approach where a quantum computer prepares a trial state and a classical computer adjusts parameters iteratively to minimize the energy. This has been demonstrated on real quantum devices for small molecules like hydrogen, H2, lithium hydride, LiH, and beryllium hydride, BeH2. Quantum phase estimation, QPE, a more powerful but resource-intensive algorithm that can precisely determine the energy levels of quantum systems. QPE requires large, error-corrected machines, so it's more of a long-term goal. The advantage of VQE is that it works with today's noisy devices, providing a testing ground for future breakthroughs. Even though current machines can only handle toy problems, they prove that the basic methods are viable. Chemistry in action. Pharmaceutical companies are watching closely. Firms like Roche, Merck, and Novartis have begun partnerships with quantum startups to explore how VQE and related methods could help simulate biologically relevant molecules. For example, one target is nitrogenase, an enzyme that bacteria use to fix nitrogen from the air. Understanding how it works at the quantum level could lead to new ways of producing ammonia for fertilizer, reducing one of the largest energy drains in agriculture. Another exciting area is protein folding. Proteins are chains of amino acids that fold into complex 3D structures, and their shape determines their function. Misfolded proteins are linked to diseases like Alzheimer's and Parkinson's, while classical AI models like DeepMind's AlphaFold have made huge strides. Quantum simulation could go even deeper, modeling folding pathways at the atomic level. Materials, science, and energy. On the materials side, quantum simulation could accelerate the search for room temperature superconductors, a long-standing dream in physics. Superconductors carry electricity without resistance, but they currently require extreme cooling. A material that worked at ambient conditions would transform power grids, magnetic levitation, and even computing itself. Battery research is another hot target. Quantum simulations could help identify new electrode materials or electrolytes that allow for higher capacity, faster charging, and longer lifespans. With electric vehicles and renewable energy expanding rapidly, this is an area with massive economic impact challenges ahead. Of course, simulating anything beyond small molecules is still far beyond our current quantum machines. Error rates, limited qubits, and short coherence times all restrict what can be achieved today. But researchers are confident that as devices scale into the thousands of qubits and beyond, meaningful simulations will become possible. One important milestone will be reaching chemical accuracy, defined as being able to predict molecular energies within about 1 kilocalorie per mole, roughly 4.2 kilojoules per mole, or 0.043 electron volts. This level of precision is required for reliable predictions in drug and material design. Hitting this benchmark on real quantum hardware would be a watershed moment for the field. Why this matters more than supremacy. In some ways, quantum simulation is a more important goal than demonstrations of quantum supremacy. Supremacy proves that quantum devices can outperform classical ones on contrived problems. Simulation proves they can do something useful, something that impacts real science, medicine, and technology. That's why many researchers and companies view simulation as the leading edge of quantum computing's practical revolution. The vision is simple. By simulating nature with nature, we can unlock discoveries impossible by any other means. From medicines that cure diseases to materials that reshape industries, quantum simulation could touch nearly every part of modern life. It's not just a use case. It may be the reason quantum computers are worth building in the first place. Artificial intelligence and machine learning already feel like futuristic technologies powering everything from chatbots to medical diagnostics. But many researchers believe that the next big leap in AI could come not from more classical computing power, but from quantum computing. The idea of quantum machine learning, QML, has become one of the hottest areas of research, promising to combine two of the most powerful technological revolutions of our time. Why AI needs help. Training large AI models is extremely resource-intensive. Modern deep learning systems require massive data sets, enormous energy consumption, and some of the world's most powerful supercomputers. For example, training GPT-scale models can cost millions of dollars and consume as much electricity as a small town. As models grow larger, the demand for more efficient training methods grows with them. Classical computers handle data by representing it in bits, but many machine learning problems naturally live in very high-dimensional spaces. Encoding and processing data in these spaces becomes extremely costly with classical methods. Quantum computers, with their ability to exist in superpositions and manipulate entangled states, may offer shortcuts. Quantum speed-ups for learning, quantum algorithms could accelerate parts of machine learning by exploiting quantum properties. For example, quantum kernels. In classical machine learning, kernels are used to compare data points in high-dimensional spaces. Quantum kernels can implicitly compute these comparisons much faster, potentially enabling new forms of pattern recognition. Quantum linear algebra. Many machine learning tasks boil down to linear algebra. Problems like solving systems of equations or performing matrix operations. Quantum algorithms, such as the Harrow-Hasidim-Lloyd algorithm, can provide exponential speedups for some of these tasks. Variational quantum classifiers, VQCs. These use quantum circuits to map data into high-dimensional quantum states, then train parameters with classical optimization to separate classes, much like a quantum version of a neural network. These methods suggest that quantum computers could one day train models faster, recognize complex patterns more efficiently, or even enable entirely new approaches to AI, where quantum AI stands today. Right now, the field is still highly experimental. Quantum devices are small and noisy, which makes running full-scale machine learning algorithms impossible. Instead, researchers focus on hybrid models, where classical systems handle most of the workload, and quantum processors tackle very specific bottlenecks. For instance, a quantum device might be used to pre-process data, find hidden structures, or speed up part of a linear algebra calculation, while the classical system does the heavy lifting. These hybrid approaches fit the NISQ era well, and may be the first place quantum AI finds real-world impact, applications in sight. Some of the most promising areas for quantum-enhanced AI include drug discovery. Combining quantum simulation with machine learning could accelerate the search for new compounds by recognizing patterns in molecular behavior. Finance. Quantum A. I could analyze enormous financial data sets to identify correlations or optimize trading strategies. Cybersecurity A. Already helps detect anomalies in network traffic. Quantum machine learning could enhance this by catching subtler patterns faster. Computer vision and natural language processing. While speculative, researchers are exploring whether quantum methods could process images or text more efficiently in high-dimensional spaces. Hype versus reality. It's important to keep expectations realistic. Many proposed quantum AI algorithms assume error-corrected quantum computers with thousands or millions of qubits, which are still years or decades away. For now, most quantum AI experiments involve toy problems with only a few qubits. Classical AI continues to advance rapidly on its own, and quantum computers will not suddenly replace GPUs or TPUs for deep learning anytime soon. That said, the synergy between the two fields is undeniable. AI can also help quantum computing by optimizing error correction, calibrating hardware, and even designing new quantum algorithms. This feedback loop, where quantum enhances AI and AI enhances quantum, may drive faster progress in both areas. The long-term vision In the long run, quantum computing could push AI into realms classical methods cannot reach. Imagine training models on data sets so large they are incomprehensible today, or recognizing structures in data that would otherwise be invisible. Quantum machine learning may not just be a faster version of today's AI. It could enable new forms of intelligence that operate fundamentally differently. For now, QML is an exciting research frontier with potential to transform industries once the hardware matures. It sits at the intersection of two revolutionary fields, and even if the breakthroughs are decades away, the pursuit is already reshaping how scientists think about computation, intelligence, and data. Quantum computing isn't just a scientific adventure. It's also becoming a global industry. What started as physics experiments in university labs has grown into a multi-billion-dollar market with startups, big tech companies, and governments, all competing for a slice of the future. The business side of quantum tells us a lot about where the field is headed, who might lead the race, and what it means for investors and industries. The big tech giants. Large technology companies have been at the forefront of quantum development. IBM has one of the most detailed roadmaps in the field, aiming to scale its superconducting qubit systems from hundreds to thousands within the next decade. Its IBM Quantum Experience platform allows users worldwide to access real quantum devices via the cloud. IBM treats quantum as part of its broader ecosystem, pairing it with AI and classical supercomputing. Google operates out of its Quantum AI lab in Santa Barbara. It grabbed headlines in 2019 with its claim of achieving quantum supremacy using the Sycamore processor. Google has since laid out plans to build an error-corrected million-qubit machine by the 2030s. Microsoft has taken a different path, betting on topological qubits, a theoretical approach that could make quantum systems more stable. Progress has been slower, but Microsoft integrates quantum services into its Azure cloud platform, preparing for the long game. Amazon doesn't build its own qubits yet, but provides access to others' hardware through Amazon Break-It, a service that gives researchers and businesses an easy way to experiment. The startups. Startups are where much of the excitement lies, as they're often more daring with their approaches. IonQ focuses on trapped ion systems. It went public in 2021, trading under IonQ, and became one of the first quantum companies available to everyday investors. Its technology boasts high fidelities and long coherence times. D-Wave, a ticker QBTS, has taken a unique path, developing quantum annealers. Instead of gate-based quantum computers, while annealers are limited in scope, they're useful for certain optimization problems and have already been applied in industries like logistics. Rigetti Computing develops superconducting qubits and also went public, making it another pure-play quantum stock. Rigetti emphasizes hybrid quantum classical computing. PsiQuantum is betting on photonics, aiming for a million-qubit system by building chips in standard semiconductor foundries. Its long-term vision has attracted massive venture capital funding. Xanadu develops photonic quantum hardware and is also known for Penny Lane, an open-source software library for quantum machine learning investment and hype. The quantum industry has drawn enormous interest from venture capital, governments, and public markets. According to market research firms, quantum computing investment has grown into the billions annually. Investors are betting on long-term payoffs, hoping to back the company that achieves practical quantum advantage first. Quantum stocks like IonQ and QBTS have seen spikes in share price whenever news about breakthroughs hits the media. In some cases, this is driven more by speculation than immediate revenue. After all, most quantum companies don't yet sell commercial products. This makes the sector risky for investors, but it also highlights how much belief exists in quantum's potential. The role of governments. Governments are not just spectators, they're active players. The U.S. passed the National Quantum Initiative Act in 2018, committing billions to research. China has invested heavily in quantum technologies, building massive labs and funding projects like the Messias satellite. The European Union has its quantum flagship program worth over €1 billion. For governments, the stakes go beyond money. Quantum computing has national security implications. Whoever controls large-scale quantum systems could potentially break encryption, dominate financial modeling, or lead in advanced materials. This makes quantum as much a strategic race as an economic one, the emerging ecosystem. Beyond hardware companies, there's a growing ecosystem of quantum software and service providers. Firms like Zapata, Cambridge Quantum, now part of Quantinuum, and Classic, focus on writing algorithms, optimizing hardware usage, and building the tools developers will need to work with quantum systems. Just as the rise of classical computing created industries for operating systems, compilers, and cloud services, quantum computing is spawning its own supporting layers. Challenges of the business model. Quantum computing companies face a unique challenge. Building hardware takes years and costs billions, while near-term revenue opportunities are limited. That's why many companies pursue quantum-as-a-service models, offering cloud access to small devices so researchers and corporations can start experimenting today. This generates early revenue while keeping the long-term vision alive, the long game. For businesses and investors, quantum is not about short-term profits. It's a decades-long play. Most startups are burning through funding while chasing milestones that may not pay off for 10 or 20 years. Yet the potential rewards are enormous. If even one use case, say drug discovery or logistics optimization, shows a clear quantum advantage, the companies leading that breakthrough could reshape entire industries. The business of quantum is still in its early stages, marked by excitement, hype, and uncertainty. Some players will fail, others will consolidate, and a few may become the Googles and Microsofts of the quantum era. What's clear is that the industry is no longer a thought experiment. It's a global market with stock tickers, billion-dollar investments, and fierce competition, shaping the race to build the future. While much of the conversation around quantum computing focuses on science and business, the technology also has profound government and military implications. In fact, many experts argue that national security concerns are one of the main drivers behind the global quantum race. From espionage to defense, quantum computers and related technologies could shift the balance of power between nations in dramatic ways, breaking encryption. The most widely discussed military application is code breaking. Modern digital security relies on encryption methods like RSA, which depend on the difficulty of factoring large numbers. Classical computers take impractically long times to break these codes. But in 1994, Peter Shor developed an algorithm showing that a sufficiently powerful quantum computer could factor large numbers exponentially faster. This means that once large-scale quantum machines exist, today's widely used encryption methods could become obsolete. Bank transactions, military communications, government files, and even personal data protected by classical encryption would be at risk. Governments are acutely aware of this. Agencies like the U.S. National Security Agency, NSA, and China's Ministry of State Security are both investing heavily in quantum research. To counter this, researchers are developing post-quantum cryptography, new encryption schemes designed to resist both classical and quantum attacks. The U.S. National Institute of Standards and Technology has been running a competition to standardize quantum-resistant algorithms, with finalists announced in 2022. But even with new methods on the horizon, there is concern that adversaries could be harvesting encrypted data now, with the intent to decrypt it later. Once quantum computers mature, quantum communication and security. While quantum computers threaten encryption, quantum communication offers new ways to secure it, as discussed earlier. Quantum key distribution, QKD, uses the principles of quantum mechanics to create unhackable communication links. China has led the way, launching the Mixius satellite and building a national backbone connecting major cities. This technology could give militaries and intelligence agencies unprecedented confidence in the security of their communications. If one nation achieves widespread quantum secure communication before others, it gains a significant strategic advantage. Quantum radar and sensing. Another area of interest is quantum sensing. Traditional radar systems work by sending out signals and detecting reflections, but they can be jammed or evaded with stealth technology. Quantum radar, in theory, could detect objects with far greater precision, even those designed to be invisible to classical radar. Quantum sensors could also detect submarines, hidden tunnels, or changes in gravitational fields. These capabilities would dramatically alter military strategy, making stealth technologies far less effective. Although quantum radar is still largely experimental, both China and the U.S. are researching it intensely. Navigation without GPS. Many modern military systems depend on GPS for navigation, but GPS satellites can be jammed or destroyed, leaving forces vulnerable. quantum technologies could provide an alternative. Quantum gyroscopes and accelerometers, which use quantum effects to measure movement with extreme precision, could allow submarines, ships, and aircraft to navigate without relying on satellites. This would make them more resilient in hostile environments. Supercomputing and simulation governments are also interested in using quantum computers for simulation and optimization. For militaries, this could mean simulating new materials for stronger armor, designing better explosives, or optimizing logistics for troop movements and supply chains. Quantum optimization could even play a role in battlefield strategy, helping commanders evaluate countless possible moves in complex scenarios. The global quantum race. The strategic importance of these applications has fueled a global quantum arms race. China has made quantum technology a centerpiece of its national strategy, pouring billions into research. Its advances in quantum communication and sensing have raised alarms in the West. The United States has responded with the National Quantum Initiative Act and increased funding for defense-related quantum projects through agencies like DARPA and the Department of Energy. Europe, Japan, and Australia are also heavily investing, often in collaboration with industry. The stakes are high. Whoever reaches key quantum milestones first could gain not just technological leadership, but also geopolitical leverage. A nation that can break encryption, secure its communications, and navigate without GPS has an edge in espionage, defense, and warfare. Ethical and strategic risks. The militarization of quantum technologies raises serious ethical questions. Should governments deploy quantum computers primarily for defense, or should global agreements limit their use, as with nuclear weapons? Some experts worry about a future where quantum breakthroughs destabilize international relations, sparking new arms races or cyber conflicts. Unlike nuclear technology, quantum computing is being developed across universities, startups, and corporations worldwide. This makes it harder to control or regulate. The line between peaceful applications and military use is blurry, and breakthroughs in one domain often spill over into the other. Quantum technologies are not just scientific curiosities. They are tools of power. From encryption and communication to sensing and navigation, they could reshape the foundations of security and warfare. Governments know this, which is why they're investing so heavily in quantum research. The global race is about more than prestige. It's about control of the next era of information and defense. Quantum computing isn't just a matter of circuits and algorithms. It also forces us to confront big questions about fairness, power, and responsibility. Like any transformative technology, it carries the potential to reshape society in both positive and negative ways. Understanding the ethical and societal implications now, while the technology is still young, may help guide how it is developed and deployed in the decades to come. Who controls quantum power? One of the most pressing issues is concentration of power. Building large-scale quantum computers requires billions of dollars, cutting-edge facilities, and world-class expertise. This makes it likely that only a handful of nations and corporations will control the most powerful systems. If access is restricted to governments and giant tech companies, quantum computing could widen the gap between those who have the technology and those who don't. This imbalance has parallels in the digital divide of the internet age. Nations and communities that lacked access to classical computing infrastructure were left behind in economic growth and global influence. Quantum computing could amplify that divide on an even larger scale if not made broadly accessible. Economic inequality and job disruption. The potential economic impacts are wide-ranging. On one hand, quantum computing could generate new industries, jobs, and scientific breakthroughs. On the other hand, it could disrupt existing systems. For example, industries built around classical cryptography may face upheaval once quantum decryption becomes feasible. Financial institutions, energy companies, and pharmaceutical firms that can't adapt quickly could lose ground to competitors who harness quantum power first. There's also the possibility of job disruption. Quantum computing won't replace most jobs directly, but it may accelerate automation in areas like logistics, finance, and data analysis. Just as classical AI raises concerns about job losses, quantum-enhanced AI could amplify those effects. Ensuring that the benefits of the technology are distributed fairly will be a major challenge. Security and privacy risks. The ability of quantum computers to break classical encryption is not just a technical issue, it's a societal one. If sensitive personal data, government secrets, or medical records become vulnerable, the consequences could be catastrophic. The transition to post-quantum cryptography needs to happen before large-scale quantum machines arrive, or else societies could face mass breaches of trust and privacy. This also raises ethical questions about surveillance. Governments with access to quantum computers could, in theory, analyze communications and data on a scale unimaginable today. Balancing national security needs with individual privacy rights will become more difficult in a quantum world. The risk of misuse. Like any powerful tool, quantum computing can be misused. In the wrong hands, it could destabilize economies, compromise national security, or even enable new forms of cyber warfare. Unlike nuclear weapons, which require rare materials and massive infrastructure, the knowledge and software for quantum computing spreads much more easily. That makes global regulation tricky. Global cooperation versus competition. One of the big ethical dilemmas is whether countries will compete or cooperate. Right now, much of the focus is on competition. Who will get there first? Who will dominate? But some argue that international cooperation is necessary to prevent misuse. Just as treaties exist to regulate nuclear arms and space exploration, global agreements may one day be needed to ensure quantum technologies are used responsibly. Access to science and knowledge. Another question is how open the field should be. Many quantum computing projects are run by universities and open source communities, sharing algorithms and results freely. But as the stakes rise, companies and governments may choose to guard their advances more tightly. This tension between openness and secrecy could shape the future of the field. Openness encourages collaboration and accelerates progress. But secrecy might protect national security interests. Cultural and philosophical questions. Quantum computing also pushes us to think about how technology interacts with culture and philosophy. The idea of machines harnessing superposition and entanglement feels almost alien compared to classical computing. For some, it raises questions about how humans understand and interact with nature. Are we prepared to live in a world where our tools operate on principles that defy intuition? Will society trust results produced by machines that even experts sometimes struggle to interpret? The responsibility of scientists and companies. Finally, there is the ethical responsibility of those developing the technology. Scientists, engineers, and corporate leaders must consider the consequences of their work. Should researchers publish every algorithm they discover, even if it could be misused? Should companies race to commercialize quantum power without safeguards in place? These are difficult questions, but ignoring them risks repeating the past mistakes where technology outpaced ethical reflection. Quantum computing holds enormous promise for medicine, energy, and science, but it also comes with risks of inequality, misuse, and disruption. The challenge for society is to ensure that the benefits are shared widely, the risks are managed responsibly, and the technology serves humanity as a whole. Whether we succeed may depend not just on how many qubits we build, but on how wisely we choose to use them. Quantum computing has been surrounded by hype since the very beginning, and with hype comes misunderstanding. Some of the most common claims about quantum computers either exaggerate what they can do or misrepresent the technology entirely. Clearing up these misconceptions is important because unrealistic expectations can damage trust and distract from the real progress being made. One of the most widespread myths is that quantum computers will replace classical computers entirely. In reality, quantum machines are not general-purpose replacements, but highly specialized tools. Your phone, your laptop, and even the world's largest classical supercomputers are not going anywhere. Quantum devices excel only at certain tasks where the structure of the problem maps well onto quantum mechanics, such as factoring large numbers, simulating molecules, or solving specific optimization challenges. For the vast majority of everyday computing tasks, classical systems remain superior and far more practical. Another misconception is that quantum computers are faster at everything. This is not true. While quantum algorithms like Shor's and Grover's show dramatic speedups, they apply to very specific problems. Many tasks see no advantage at all from quantum hardware. In fact, for basic arithmetic or text processing, quantum computers would likely be slower due to overhead from maintaining delicate qubit states and error correction. The power of quantum lies not in universal speed, but in targeted breakthroughs for problems that are otherwise intractable. There is also confusion around quantum supremacy. When Google announced it had achieved this milestone in 2019, many people believed it meant their machine could outperform any computer on Earth at useful tasks. What it actually demonstrated was the ability to perform a highly specific, contrived calculation faster than classical supercomputers. The result was scientifically meaningful, but it did not mean quantum computers were suddenly ready to revolutionize the world. Supremacy is a milestone, not an endpoint. A common myth is that quantum computers are already breaking encryption. In reality, no existing machine comes anywhere close to having enough qubits or stability to run Shor's algorithm at the scale needed to factor modern encryption keys. The risk is real for the future, but for now, classical encryption remains safe. This misconception likely arises from both media hype and the natural fear surrounding cybersecurity. The urgency is to prepare encryption systems before quantum machines become powerful enough, not because they already are. Some people imagine quantum computers as mysterious black boxes that can try all answers at once and instantly solve any problem. This idea comes from oversimplified explanations of superposition. While it is true that qubits can represent many possible states simultaneously, extracting useful information from that superposition is extremely difficult. Quantum algorithms must be carefully designed to steer the probabilities toward the correct solutions. Without that, the output is essentially random noise. In other words, quantum computers are not magic. They are clever tools that need precise guidance. There are also myths about how close we are to fully working quantum machines. Optimistic headlines sometimes imply that large-scale, error-corrected quantum computers are just around the corner. In truth, building a device with millions of stable qubits may take decades. Current systems are in the noisy intermediate stage, with only a few hundred qubits and significant error rates. Progress is steady and encouraging, but it remains a marathon, not a sprint. On the flip side, skeptics sometimes claim that quantum computers will never work at all, dismissing the entire field as hype. This, too, is inaccurate. Small-scale quantum machines have already been built, tested, and shown to perform computations that align with theory. While scaling up is daunting, nothing in physics rules it out. Dismissing the field entirely ignores the very real progress achieved by scientists and engineers around the world. Finally, there is a cultural myth that quantum computing is beyond human understanding, accessible only to geniuses. While the physics is indeed complex, the core ideas can be explained in accessible ways. Concepts like superposition, entanglement, and interference may sound abstract, but with careful teaching, they can be understood by anyone with curiosity. Treating quantum as an impenetrable mystery only reinforces a false barrier between science and the public. Separating fact from fiction helps set realistic expectations. Quantum computers will not solve every problem. They will not replace classical machines, and they are not arriving tomorrow in their full form. At the same time, they are not vaporware or fantasy. They are real devices being improved step by step. The truth is more nuanced and more interesting than either extreme. Quantum computing is one of those rare fields where science, technology, philosophy, and society all intersect. It started as a theoretical idea born out of frustration that classical computers could not efficiently simulate quantum systems. In just a few decades, it has grown into a global endeavor involving universities, corporations, and governments racing to harness the strange rules of quantum mechanics for practical use. Looking back, the story of quantum computing is a story of persistence. Early on, many thought the idea was too abstract or the engineering too impossible. Qubits are fragile, entanglement is difficult to sustain, and error correction seemed out of reach. Yet, step by step, researchers overcame barriers that once looked insurmountable. Today, we have devices with hundreds of qubits, cloud platforms that let anyone run quantum experiments, and real-world algorithms being tested on hardware that seemed unimaginable only a generation ago. The progress is real, but so are the limits. Quantum computers are not ready to revolutionize everything tomorrow. They remain noisy, expensive, and constrained. Scaling up to fault-tolerant machines with millions of qubits will require breakthroughs in hardware design, error correction, and architecture. This could take decades. But the timeline does not diminish the significance of what is happening now. Every milestone, from simulating a small molecule to demonstrating quantum advantage on new problems, is a step toward a future that will reshape science and industry. What makes quantum computing so captivating is not just its technical promise, but its implications. It forces us to rethink security, since today's encryption could be vulnerable in the future. It challenges industries to prepare for disruption, from drug discovery to finance. It even sparks philosophical reflection on how humans interact with machines that operate under rules we barely grasp intuitively. The idea of a computer that works by exploiting the fabric of reality itself pushes us to expand our imagination. There is also an element of humility. Quantum mechanics is famously counterintuitive. To build technology on top of it requires accepting that the world does not always conform to common sense. Quantum computing teaches us that progress sometimes comes not from forcing nature into our frameworks, but from working with nature as it truly is, even when it defies our expectations. The future of quantum computing will likely be uneven. Some nations and corporations will push ahead, while others may lag. Some applications will prove wildly successful, while others will fizzle out. The technology may creep into our lives gradually, at first through niche scientific and industrial uses before eventually becoming part of everyday infrastructure. Just as few could have predicted how the internet would transform society, it is impossible to map exactly how quantum computing will reshape the decades ahead. What is clear is that quantum computing is no longer just an idea. It is a reality in progress, a living experiment with the potential to unlock discoveries across science, medicine, energy, and beyond. Whether it takes 10 years or 50, whether it fulfills all expectations or just a fraction, the pursuit itself is one of humanity's boldest attempts to turn the strangeness of the universe into a tool. In the end, the value of quantum computing may be more than just practical. It is also symbolic of what humanity can achieve when curiosity drives us beyond the familiar. It shows that even in a world filled with powerful classical computers and advanced AI, there is still room to dream bigger, stranger, and deeper. The journey into the quantum realm is just beginning, and whatever comes next, it will remind us that technology is not only about solving problems, it is about expanding the horizons of what is possible. When most people think about quantum computing, they imagine the hardware, the cryogenic refrigerators, the superconducting circuits, the delicate ions held in place by lasers. But the other half of the picture is just as important: the software. Without programming languages, algorithms, and frameworks to control these machines, the hardware would be little more than a scientific curiosity. Programming a quantum computer is fundamentally different from programming a classical one. In a classical system, you give instructions that tell the computer to perform specific operations on bits: add, subtract, store, retrieve. In a quantum system, the instructions are quantum gates, which manipulate the delicate state of qubits. These gates don't flip bits from 0 to 1, but instead rotate qubits into superpositions or entangle them with one another. What makes this tricky is that quantum states cannot be directly observed without collapsing them. That means you cannot peek at the intermediate steps of your program in the same way. You might debug a classical code. Instead, you must design algorithms that steer qubits toward useful outcomes, knowing that measurement at the end will collapse their states into classical results with certain probabilities. This requires a different mindset for programmers, who must think in terms of probabilities, interference, and optimization. Several programming languages and frameworks have emerged to make this process accessible. One of the most widely used is Qiskit, an open-source toolkit developed by IBM. With Qiskit, programmers can build quantum circuits, simulate them on classical computers, and then run them on real IBM quantum devices through the cloud. Another popular option is Cirq, developed by Google, which is tailored to the company's hardware and focuses on near-term algorithms for noisy devices. There are also domain-specific frameworks. Penny Lane, created by Xanadu, focuses on quantum machine learning and hybrid algorithms. It integrates smoothly with classical AI libraries like TensorFlow and PyTorch, letting developers combine quantum and classical methods in one workflow. Forest from Rigetti and Ocean from D-Wave target their own hardware platforms with libraries designed for optimization problems and annealing. A common theme among these frameworks is the hybrid approach. Because quantum devices are still small and noisy, most useful applications today combine classical and quantum computing. For example, a classical optimizer may adjust the parameters of a quantum circuit in a loop, using the quantum processor to evaluate certain states. These are called variational algorithms, and they form the backbone of much of today's quantum programming. Another layer of quantum software involves abstraction. Just as most classical programmers don't need to know how a transistor works to write code in Python, future quantum programmers shouldn't need to understand every detail of qubit physics. Higher-level languages and compilers are being built to translate human-readable code into the precise pulses and gate sequences needed to run on hardware. This makes the technology more accessible to people outside physics, opening the door to chemists, biologists, and engineers who want to apply quantum tools in their own fields. There is also the challenge of benchmarking and simulation. Because real quantum devices are limited, much of the testing is done on simulators. Classical computers that mimic quantum behavior up to a certain scale. Simulators allow developers to experiment with circuits, understand how errors accumulate, and test algorithms before running them on expensive hardware. However, because classical simulation becomes exponentially harder as the number of qubits grows, these tools hit limits quickly, reinforcing the need for access to actual devices. The quantum software ecosystem is still young, but it is expanding rapidly. Universities are offering courses in quantum programming. Coding boot camps are starting to include Qiskit and Cirq, and even high school students are experimenting with building their first quantum algorithms. This democratization is important because the future usefulness of quantum computing depends not only on physicists who build the machines, but also on the programmers and scientists who will use them to solve real problems. In many ways, the current state of quantum programming resembles the early days of classical computing, when punch cards and assembly languages were the norm. Over time, classical computing evolved into the high-level programming environments we take for granted today. Quantum computing will likely follow the same trajectory, moving from handcrafted circuits to user-friendly languages and automated compilers. One day, writing a quantum algorithm may be as simple as importing a library and calling a function, with the underlying system deciding how to distribute the workload between classical and quantum processes. The story of quantum computing is not only about qubits and cryogenics. It is also about building the tools that let humans communicate with these machines. The software bridges the gap between abstract quantum mechanics and practical problem solving. Without it, even the most advanced quantum hardware would sit idle. With it, we begin to unlock the real potential of this strange and powerful new way of computing.